Okay, today we'll analyze diode circuits, including rectifiers, and then we'll get into Zener diodes, and then, if time permits, Zener regulator, analysis of Zener regulator. So first up is diode rectifier circuits. And this is the primary application for diode. Okay, it's a one-way device, right? A diode is a one-way device, and that's the most critical aspect in this application. Actually, in most applications of diodes. So we can create a AC to DC converter known as a rectifier. The name rectifier comes from the fact that it seems as if there's something wrong with AC, so we are rectifying it and finding a solution by converting it into DC. Almost all appliances and consumer electronic devices that we use today are all run on DC. Okay, our smartphones, especially our mobile devices, built-in batteries in smartphones, laptops, tablets, everything runs on DC. We need to convert the power outlet that's on AC, and that's where our laptop adapters and chargers come into the picture. So each laptop adapter or charger is an AC to DC converter. Okay, AC to DC converter. Now, that would beg the question, why wouldn't we just distribute power or electrical energy as DC? Why do we send it out at AC? Well, in the early days of electricity, mass production of electricity, there was this technology war that came to be known as the current war. And I believe I had a slide early on in the chapter that I showed you, right? There was AC versus DC. It was still being formulated, and there were competing technologies backed by competing researchers and scientists, which were further backed by competing corporations or business interests. And on one side, we had Tesla, Nikola Tesla, who was backing AC, and the other side, we had Edison, who was backing DC. DC had a lot of problems, namely in distribution. It's not as easy to step it up or step it down compared to AC. And so AC won the war, and all power distribution from that point on was always in AC. Okay, because it is easy to step up or step down an AC voltage or current simply by using a transformer. So all of electrical power generation and distribution is always in AC, but most of our consumer usage is all in DC. So first up is the half-wave rectifier. It is so called because it rectifies only half the AC input cycle. Okay, only half the AC input cycle. So here's the circuit, and what I'm going to use is the ideal diode model to explain the operation of these circuits. Diode D1 is connected to an AC input. This is the load resistor R on the far right. Simple series circuit. You have an AC input passing through single diode going towards the resistor. AC input signal is shown here. We can also model this as a positive supply in the positive half cycle and negative supply in the negative half cycle. Terminals will be flipped. So that's what I show on the diagrams on the left. So this is the positive half cycle right there, and this is the negative half cycle. Okay. In the positive half cycle, sinusoidal waveform is going positive. That means the anode is at a higher level than the cathode. And when the anode is higher than the cathode, diode turns on. When the diode turns on, why is this? When the diode turns on, we can model the circuit as we can model the diode as a short circuit, and the input reaches the output. Okay. If it's an ideal diode, then at the output, we get the exact same voltage value as V in. So since I'm using an ideal diode model, V out is exactly equal to V in the positive half cycle. In the negative half cycle, we can model it as a voltage source with its polarity flipped. Now, the cathode is higher than the anode. And because the cathode is higher than the anode, the diode is off. We can model it as an open circuit. V out is equal to 0. Okay. So for positive half cycle, diode is on. V out is equal to V in. Negative half cycle, diode is off. V out is equal to 0. Hence, the name half wave rectifier is only rectifying or converting half the AC into DC. All right, let's take a pause. Let me know if you have any questions. Yes. When you want to build a really cheap, inexpensive, low quality adapter, which for the most part, I haven't seen one of those in more than 30 years. Yes. So the question being asked is, if the frequency is high enough, can we model it as a DC? So, and I will explain a little bit more about how and why this can be called a DC versus AC. But yeah, sure. If the frequency is high enough, yes, we can do that. Because the average energy that is being transferred is now high enough. But again, we have to keep in mind AC to DC conversion. Most of the conversion or most of the application is for standard power outlets, which is 60 hertz in North America, 50 hertz in the rest of the world. So it's a very, very, very low frequency. Yes. Is the RMS voltage supplied by the input or the output? We wouldn't need to take the RMS or the output. We could simply take the average value of the waveform. The reason we take RMS is because the AC signal is equally split in the positive and the negative values. Okay, so the main question, the most common question would be, how is this waveform DC? Right? It's still changing its value, even if it's just positive half cycle. We still have like positive square waves. It's an AC waveform. So how is a half wave rectified waveform, how is this considered to be DC? And the answer is yes. I mean, it should not be. I mean, I like to call it like pseudo DC. It's not really DC. It's still AC for all intents and purposes, right? So the answer to that is, if you take this output, if you take this V out, connect it to a meter and measure like AC RMS value, it's going to give you some AC RMS value. And if you measure the DC value, it's going to give you some average DC value also. Okay. But again, you have already noted the drawbacks from the questions that are being asked here. You already noted the drawbacks, right? It's off. And hence we have what are known as full wave rectifiers. Oh, I skipped over on this slide. So this is a half wave rectifier by using the constant voltage drop model. Okay. The only difference is, of course, instead of ideal diode, I'm using a constant voltage drop of 0.6 volts. That means 0.6 volts of my input Vs is used to turn the diode on. Okay. So my output V out is less by 0.6 volts. Output V out is less by 0.6 volts. And let's see, VDC is considered as the peak minus V on diode on voltage. And there are other equations that we'll look at in just a few slides. Okay. All right, half-wave rectifier. So half-wave, sorry, not here. Full-wave rectifier. Come back to the filter capacitor later. The full-wave rectifier, this also is not as common as it used to be in the past. But the full-wave rectifier is basically two half-wave rectifiers connected in sort of parallel. Not quite parallel, but it's two half-wave rectifiers with a load resistor in the middle, and it requires a special kind of transformer. It's known as a center tap transformer. Assuming everybody's familiar with transformers from EE212, right? So you have a step-down transformer is two inductive coils wound around the same core, wound around each other. So input goes to primary coil, output is taken from the secondary coil, and depending on the number of turns of those coils, depending on the ratio, the voltage from the input side is either stepped up in value at the output, or it's stepped down in value. So at the consumer end, meaning at our end, when we plug something into the wall, we always use a step-down transformer. The power supply voltage is stepped down to whatever our requirement is. Now, if you put a secondary tap, if you put a tap in the secondary winding, meaning you take an output, and let's say it's exactly in the center of the secondary winding, now you've divided that secondary winding into two parts. And it looks like this. So every single half cycle, you have a positive negative for diode D1, you have a positive negative for diode D2, and then every negative half cycle, it flips. In negative half cycle, the polarity would reverse. So the analysis using idle diode or constant voltage model would be exactly the same as the half-wave rectifier. In the positive half cycle, diode D1 is on, like a half-wave rectifier. It conducts current through the load resistor, causes a voltage drop with a plus on the right and minus on the left. In the negative half cycle, diode D2 is on because the polarity is flipped. Circuit looks like this. Polarity is flipped. Current is still flowing in this direction. So if you notice the resistor, the current through that load resistor flows in the same direction for both the positive and the negative half cycles. Okay. The resistor is shown right here, connected to ground, so it's a straight connection, and that's what I've shown here. In the positive half cycle, diode D1 is on, D2 is off. You get the positive half cycle at the output. In the negative half cycle, the polarity reverses, so D2 is on and D1 is off. Current flows in the same direction. So both half cycles, the load resistor sees the same direction of the current and hence the same polarity of the output voltage. So both half cycles are rectified. Let's take a pause, think over this, and let me know if you have any questions. Yes. This one? I will finish the analysis of all three rectifier circuits first, and then we'll talk about filter capacitor. Yes. So center tap transformer is basically, this question being asked is about a center tap transformer. So you have a transformer. This is the primary side where the input's going in. And this is the secondary side, output. Okay. A tap is basically connection. you're poking into the secondary winding and taking out a connection. So if you take out a connection and you make that connection directly in the center of the winding, the turns ratio is now divided. And because the turns ratio is now divided, and of course, we'd have to go back to 212 to look at those equations. And what was I saying? I lost my train of thought. V1 over V2 is N2 over N1. Remember those equations? And so these connections act as two separate coils. And so when you tap it in the center, the effect is such as if there are two coils connected in series, which are then wound around the primary coil. So when you make a connection on the secondary winding, the polarity appears as if it's connected in series. It's plus minus, plus minus. And center tap is just one kind of tapping. When I was a student, this is more than 30 years ago, I had a transformer, or I mean, I had a variable power supply. Manually, you could change the dial. And so I used it for a few years, and then I wanted to see what was going on inside. So I just opened up the transformer in there with multiple windings in the secondary coil. And there's a dial on the front that you simply, let's say, another here, 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 here. And all of these are connected in some sort of mechanical dial. It's like a switch. You move the switch, and depending on where it makes contact, you're seeing a small portion of that secondary winding. As you could get an output of like 1.5 volts, 3 volts, 4.5 volts, 6, 9, 12, 15 volts. So multiple taps in the secondary winding. But that's what it means. You had a question?
So what's the time the like I don't see why you'd want to bias one portion of like the wave cycle, so the input wave cycle for the person. So it's basically just like on the right hand side, like an auto transformer, and on the left hand side, like a those two like a parallel computer. You have like a series stack transformer, but they have to have the same temperature.
You're talking about a single center tap? So this?
Well, so like when I see like that double bar.
Uh-huh. Oh, this. That's just a symbol for a transformer. It indicates the core.
Okay, but
You have two inductive windings around the same core. That's the standard symbol of a transformer. This is a transformer. V2, yes. So the question, if I understand your question correctly, is why use a center tap? Or maybe I'm confused. Okay, yes. Uh-huh. No, no. It's still the same transformer, it's just multiple connections. A tap simply means a connection. And as a step down transformer, we are stepping down from our power outlet all the way down to like 20 volts or less. So it'll always be a step down transformer. So winding will never be equal. If the winding is equal, then if we apply 120 volts from our power outlet, the output of the transformer is also 120 volts. So it's a step down. So winding coils, the turns ratio would never be equal. But the obvious disadvantage here is that you need a special kind of transformer. So create another circuit called a bridge rectifier. This is by far the most common one. You have 4 diodes connected in a bridge configuration. And these 4 diodes are connected again to an AC input. In this case, the transformer is nothing special, just a simple step down transformer, depending on our output requirements. And you connect a load resistor. So the way you would want to build this circuit, and you're going to do this in next week in the lab, is you keep an eye on this. The bridge configuration, you have 4 points. And I typically always like to remember it like this. You have 2 diodes pointing up, and you have 2 diodes pointing down. And what this does is, if you look at the 4 nodes, 2 of the nodes, which is right here and right here, what do you see about the terminals with respect to anode cathode? So here and here. Those 2 nodes, yes. Yes, they're different. So one cathode meets one anode. That's where the input goes in. Okay, that's where the input goes in. So if you are building the circuit, V in goes where the anode meets the cathode. And the output is taken across the 2 nodes where 2 cathodes meet and 2 anodes meet. And so you simply place a resistor right there. And that's it. That's how you remember a bridge configuration. And the output where the 2 cathodes meet is the positive end, and the output where the 2 anodes meet is the negative end. And you see that reflected here. This is simply connected like this, right? Shows the ground line and shows here. But this is far simpler for explanation purposes. Your input goes in, anode cathodes, output's taken across the other 2 nodes. So the explanation is right here. Let's say we are using the ideal diode model again. Positive half cycle, plus is at the top, minus is at the bottom. Diodes D1 and D2 are off. Sorry, D1 and D3 are off. D2 and D4 are on. Everybody see that? Right? And so current is going to go flow in this direction. And through the resistor, it's entering from the right, causes a voltage drop with a plus on the right and minus on the left. Negative half cycle, polarity reverses. Diodes D1 and D3 are now on, and D2 and D4 are off. Current flows in this direction. It's still flowing from right to left, so causes a polarity voltage drop with a minus on the left and plus on the right. Yes. Uh, this or this on the right. That's so the question being asked is, why is it in this sort of weird configuration? Like compared to this, is just for explanation purposes. It makes it easier to explain. If I have something like this, and in the past, I've kept it like this and explain it, how current goes through here, just with a simple arrow, some students would get confused on, how the circuit is actually working. I would say D2 and D4 are on, and the current goes through here. But then, our brains automatically look for a closed path, even though we can see that this is connected here. So it just makes this easier to explain if I use this model. That's all it is. So I redraw the circuit like this. Circuit's exactly the same. There is no difference. Resistor is connected to the two cathodes and the two anodes. Also, more importantly, this is how you will build your circuit in the lab. You'll need two wires coming out of the diodes where you will place or connect the resistors and the capacitors. So it just makes it easier to explain. These are just illustrations. The diodes and the resistors themselves don't, they don't know anything on how they're connected. This is just, again, for explanation purposes. But the most important point here is we require two diodes for each half cycle. And the bridge configuration allows us to do this. When you have a bridge configuration and you have the resistor in the middle of that bridge, the current flows in the exact same direction for both positive and negative half cycles. So in the positive half cycle, D2 and D4 are on. In the negative half cycle, D1 and D3 are on. Thus, both half cycles are now rectified. The current flows in the exact same direction, so V out has the same polarity. So when we look at V out, we see simple mountains like this. Full wave rectified output. Okay, full wave rectified output. Let's take a pause. Let me know if you have other questions. Yes. So that's to do with the filtering, and I'll get to that just as soon as we are done with this. Everyone understand the operation? Okay. So as we can see, this is still not quite DC, right? It's not DC, it's still fluctuating voltages. So there is an average level, but if you want to create a flat line, what we do is we use a energy storage component. Capacitor is the cheapest and the easiest to actually connect across our load. So let's say instead of a resistor, we connect a capacitor at the output. Okay, just a capacitor, nothing else. What happens? When the first positive half cycle arrives, diode turns on, capacitor starts charging. Capacitor reaches full charge. Depending on the size of the capacitor, depending on the voltage that is being applied, it might charge up in the first half cycle, or it might take a second half cycle to reach full charge. But it happens very, very quickly, right? 1/60th of a second. So as soon as we turn the switch, capacitor is fully charged. That's what we see. Once the capacitor is charged, and I'm looking at this waveform here on the right, it reaches full charge. And that's what's shown here, full charge. Negative half cycle, diode turns off. Capacitor will hold the charge across itself. Right? Negative half cycle, capacitor will hold the charge across itself. Diode is now open circuit, or in this case, if I was using a practical measurement, then I would say it's a very high resistance. Right? Very high resistance. Ideal diode, it's an open circuit. Real life diode, reverse saturation current, very high resistance. Capacitor is disconnected or starts to discharge slowly through that resistor or through that diode. So here's that discharge line. So capacitor starts discharging. Eventually, if we just leave it alone, it is going to discharge all the way to 0. But before it can do that, right up to here, this point, the next positive half cycle arrives, capacitor starts charging again. So capacitor starts charging, then it begins to discharge. And before it can go all the way to 0, the next positive half cycle arrives and it starts charging again. So depending on the size of the capacitor, in the negative half cycle, the empty space between the two cycles the energy is now provided by the capacitor, thus raising the output voltage levels. And that's how we use capacitor's energy storage function as a filtering. The reason it's called a filter capacitor, because it is filtering out the AC component and bringing it as close to DC as possible. Does that make sense? Yes. Yes. Ideal diode, it would not discharge at all. It would be a flat line, really flat line. And this is just, of course, just a capacitor. In real life, of course, you'd have a load resistor and you'd connect a capacitor in parallel with that load. But the point still remains. Tristan, you had a question? Okay. Does everybody understand the fundamental operation of the capacitor? So because the capacitor is not, it's not ideal, right? So it's not a flat line. Going back to your point, as you said, it's discharging slowly. But if it was ideal, it wouldn't discharge at all. It would remain a flat line. So it still leaves behind some AC component. And this is completely exaggerated. The size of that peak where it's still empty, like right here, this is empty portion, right? That's that empty portion. That is very small compared to your output. Typically it's in millivolts compared to like tens of volts. Okay, so it's very, very small. So this is exaggerated, but it is still present, and it looks like the surface of the ocean, ripples of waves. Hence, it is known as the AC ripple or AC ripple component of your DC waveform. So now the waveform, which was just peaks of AC, the level has now risen up and it's almost close to being a flat line. And goes back to an earlier point that you made. If the frequency is high enough, then the charge and discharge cycles are going to be very, very close together. So again, that would be almost flat. So there are a couple of quantities that you look at is basically the conduction time and the conduction angle for the rectifier. Equation for the ripple voltage is given here. V peak, that's basically the output peak voltage minus the voltage as required to turn on. If it's ideal diode, it's 0, constant voltage drop, 0.6 volts. If it's not specified as a student, if you're trying to solve a problem, it more likely than not will be specified in the problem statement. If it's not specified, you can assume whatever you want. You can assume 0.6, assume 0.7, and then perform your calculations using those assumptions. And then T is the time period. For all intents and purposes, would be 60 hertz or 1/60. And then RC would be the RC time constant for the resistor and the capacitor. The R would be the load resistor. If you have a diode and you connect a resistor, load resistor right here, the capacitor would discharge through that load resistor. So that would be the RC time constant. Yes. VS, the applied input voltage from here. VP is basically V in, that's coming into the half-wave rectifier. Diode on voltage, yes. Diode on voltage. DC current, VP minus V on divided by R. And then, excuse me. And then capacitor value can be determined from this equation right there. So design we can design a power supply based on the minimum ripple or the maximum ripple that we want for our application. Okay. The same thing applies for a center tap and for a full wave rectifier. In this case, the frequency of the output is now doubled, right? And again, this is something you can note when you're in the lab. If you look at the frequency of half wave rectifier, the outputs of the half wave rectifier and the frequency for the output of the full wave rectifier, you'll see 60 and 120, which makes sense, right? So time period, of course, is now half, and the ripple would also be smaller because instead of discharging all the way here, it starts charging again. So the empty spot, instead of being this, is now only 1/2 cycle. So frequency has doubled, 120 hertz versus 60. Ripple also is now lower or smaller. So that's another advantage of using a full wave rectifier versus a half wave rectifier. Okay. Same thing here, and same thing for a full wave rectifier. So all of these equations are there in the book. Yeah, I have them listed here. And there's also a comparison table that I had for these equations right here. Okay. Filter capacitor, Vp minus V on over Vr, and T over 2R. Peak inverse voltage is how much voltage the diode needs to accept without breaking down in the reverse bias. So every single negative half cycle, the diode will be reverse bias. And in that reverse bias, we need to ensure that the diode is capable of handling that voltage. Okay, for the most part, it's not a problem. Most rectifiers use not the modern chargers, but most standalone rectifiers in the past use the 1N4000 series. And the lowest end, 1N4000, can handle up to 50 volts in reverse bias. So you could create a power supply up to 20, 25 volts, and it would be fine. The highest of them, 1N4007, can handle up to 400 volts in reverse bias. So you could directly stick it into the wall, as we do with modern chargers. The modern chargers are, it's interesting, the design. Whoever came up with it would take a power outlet, rectify it. So there's diode right at the front end without stepping down the voltage. You're rectifying 120 volts. Convert it into DC or pseudo DC, and then invert it to get an AC output again. So you take the DC, step it down, convert it into high frequency AC, and with high frequency AC, you can use a very small transformer for the same resulting voltage. But again, that's a separate discussion. Yes. So question being asked is about, doesn't it depend on the source of the input voltage? The answer is yes. So if you use a transformer, the input to the transformer is not the input to the diode circuit. The output of the transformer is the input to the circuit. So when we state Vp, we are referring to the input to the diode circuit, not the input to the transformer. Uh-huh. Yeah, the input voltage would be Vp, right? V in, V of t is Vp sine omega t, the peak value of the input voltage. Yeah. Are you thinking in terms of 120 volts? Let's go back. So here's the transformer. All three circuits, doesn't matter. Here's the transformer. This, let's say we are in North America, it's 120 volts. If you're outside of North America, it's 220 volts. But let's say we are in North America, you're plugging the transformer into the wall, that's 120 volts. That's not V in to the diode circuit. V in is right here. That's the output of the transformer. That depends on our application. If our application required 20 volts, we'd make sure the transformer was 20 volts. And that's the VP. Does that make sense? No, that's the desired breakdown voltage. This PIV rating is basically an indicator. Like the diode that we use for the application must be at least twice the VP that we are applying into the circuit. Bridge rectifier, there are two diodes for each half cycle. So the voltage is divided serially across each diode. And so just V peak is fine. But as I just stated earlier, most of the power supplies that you'll be working with would be 10 volts, 12 volts or less. Consumer devices, 5 volts, right? Any adapter that we plug in, the output of that is 5 volts. Well, unlike it's a USB-C power delivery. But if it's 5 volts, your diode just needs to be able to handle maybe like 10 volts in reverse bias. That's it. Wouldn't be larger than that. There was a hand raised here. Yeah. At the front end of every device that we ever use. So if you're up, huh? No, 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 no. It's in the, so let's say I have, we have our smartphones, we have our laptops, right? So laptop adapters are heavier. There's a lot more going on inside a laptop adapter. You know, there's SPSS power supplies and there's lots of different things in there. But the reason it's heavy is because there's a transformer in there. Mobile chargers, like tablet chargers, they are not as heavy because, again, as I said, there's a different kind of circuit in there where we rectify directly first, then we step it down, and then we convert it back into AC at a high frequency. So it's very different. But any other device, like you say, we take this monitor, plugs directly into the wall. There is a power supply built in here because there is space enough. You don't need to save space. Projector that we see in the wall here, compared to the the lamp and the associated circuitry, the power supply of the transformer is far smaller. So we don't need to conserve space in there either. And so there's a full-fledged transformers inside all of those. So whether it's a desktop PC, computer, all has its own built-in power supply. Years ago, when I was a brand new grad student, I saw a Pentium 100 compact laptop. It had a power supply built in. You could plug it directly into the wall. Like heavy as. It was really heavy. It's about 10, 12 pounds. But it was like an old device that somebody had thrown out. So I was just taking a look at it. But yeah, it was like any other like monitor. You could simply plug it into the wall. It had a transformer inside. But pretty much every device that we use, if it runs on DC, any appliances, if it has a DC motor in it, there will be a rectifier circuit in there somewhere. Yeah, that's why they always they used to be on the picture tube televisions, CRT cathode ray tubes. I mean I have a diploma in like electronic servicing from a long time ago, so we worked with those. You open it up, the first thing they say is high voltage because there is the power goes directly into a power supply board. The power supply board sends it's different levels of voltages that goes everywhere, but one thick cable goes directly onto the side of the tube. It's about few thousand volts inside your television. That's why they always had that say, do not open it up. It's to accelerate the beam that goes on the tube because it's scanning from it. Anyway, Yeah, if you can get a hold of one of those old ones, you can take it, open it up, take a look. Don't plug it into the wall. Yeah, Zener diode. Okay, so there's not enough time to go through the problem, but I want to just go over some of the basics here. Okay, so if you notice the polarity of these voltages, this is a Zener diode circuit, right? So we're analyzing the Zener diode and determining the Q point using the load line analysis. The Zener diode operates in the breakdown region. If the Zener diode is forward bias, it works like a normal diode. It works like a normal diode. It's only in the reverse bias. It's only in the reverse bias that we're interested in. Forward bias, it's like a regular diode. In the reverse bias, it breaks down because it is very heavily doped. And so it doesn't conduct until its breakdown voltage, then it turns on and remains a near flat constant line. Not flat, sorry, near vertical straight line. This is exaggerated. The voltage does not change that much. Okay, it's almost like a sharp drop, almost as close to ideal as possible. So I will analyze this next class on Monday, but what I wanted to point out is this. Zener is used in reverse bias. Okay, so we have two terms associated with it, VZ and IZ. Zener voltage, and there's also IZ, which is Zener current. The polarity of VZ and IZ, is opposite to the diode voltage and diode current. You had a question? This one? Will, yeah, the line would be steep. What do you mean? Into the first quadrant? Here? Oh, this way. No, actually, that's the point I'm making. Zener is used in the reverse bias, so it's plotted in the third quadrant. So it's always negative V and negative I, because if you look at the diode by itself, it is used in reverse bias, meaning the cathode is connected here to the positive end of our power supply. And the anode is connected towards the negative end of the power supply. So if we just refer to the Zener diode itself as a diode, not as Zener or anything else, just the diode, reference for the diode is anode positive, cathode negative. And hence VD for a Zener diode remains the same. Positive at the anode, negative at the cathode. Current ID also maintains the same flow, flowing from anode to cathode. But as part of the circuit, VZ will be plus here and minus here, opposite to that of the diode itself. And current IZ flows in this direction. See, the device itself doesn't know what is forward bias, what is negative, or what is reverse bias. The plus and minus signs are for us. Otherwise, our equations would never balance out. If we take this polarity into account, right there, our KVL would not work. As simple as the circuit is, you have one voltage source. There's only one source in there. So that voltage must be dropped across the resistor and must be dropped across that Zener diode. If we use the diode polarity and the diode current right there, KVL would not work. And that's the thing I wanted to point out before we do analysis on Monday. Okay, so it is opposite. VZ would be plus at the top, minus at the bottom, but diode voltage is negative. So when we plot it, we are simply plotting the Zener diode characteristic. So it's minus V and minus I. We plot it in the third quadrant, even though we'd say VZ is 5 volts. So we would say VZ is 5 volts, so it means plus 5 volts. But when you plot it, you would plot VZ as minus 5 volts. Whatever positive current you get through there, we say current is, let's say, 1 milliamp through the Zener diode. So IZ is 1 milliamp. It's still plotted in the third quadrant. So we plot IZ as minus 1 milliamp, or basically this way. Think on that, and then we'll continue this discussion on Monday. Okay, Friday quiz today and Monday quiz. There should be a homework due for rectifiers. And I'll be in my office this afternoon, but I'll be in and out a little bit. So if you have any questions, actually, no, I won't be in and I'll be there. So if you have any questions, feel free to stop by. Yes. Uh-huh.